In the world of energy supply, there is a relatively new and highly efficient player known as the Combined Cycle Power Plant, or CCPP for short. But what makes it so special? Simply put, a CCPP takes the best features of gas turbines and steam turbines and combines them into one single system. By doing this, it provides electric power at a much higher efficiency than either of those systems could ever achieve on their own. In this video, we are going to look at the typical processes gas and steam turbine plants. We will then summarize how these two separate processes work together in a typical combined cycle setup. We won't get bogged down in every tiny bolt and wire. Instead, we'll focus on the major components that are essential to understanding the overall process. Let's start with the gas turbine power plant. The goal is to convert chemical energy into mechanical energy, and finally, into electrical energy. To supply electricity from a gas turbine plant, several key components must work in harmony. First, we have the gas turbine itself, which is connected to a generator. Supporting these are the exciter, generator bushings, and the generator breaker. To ensure the power is ready for use, we use a generator step-up transformer and finally, a grid breaker to connect to the outside world. Each of these plays a vital role in keeping the lights on. Now that we've identified the main players in the gas turbine section, let's take a closer look at what each one actually does. To understand how a gas turbine actually creates power, we need to look at its three main processing elements: the air compressor, the combustion chamber, and the turbine itself. These three parts work together in a continuous cycle to turn fuel into motion. It all starts with the compressor. Its job is to take mechanical energy and convert it into pneumatic energy, basically, high-pressure air. It uses a series of rotating and stationary blades to squeeze the air down. Interestingly, the compressor is actually driven by the turbine through a common shaft. Aside from fueling the fire, some of this pressurized air is also used for cooling and sealing the internal parts of the set. Next, that pressurized air is delivered to the combustion chamber. Think of this as an enclosed, pressurized, firing place. Here, liquid or gaseous fuel is continuously burned, converting the chemical energy of the fuel into intense heat. This creates the high-energy combustion gas needed to drive the next stage. Now we reach the turbine itself. This is the prime mover that drives both the generator and the compressor. The hot, compressed gas strikes blades mounted on a rotor, causing it to spin. This converts thermal energy into the mechanical energy we need at the coupling. Once the gas has passed through the turbine and did its work, it is discharged into the atmosphere as exhaust gas. Of course, we need to control how much power we're producing. This is handled by fuel throughput control. Using specialized control valves, we can adjust the fuel flow to any position between fully open and fully closed. This allows the plant to hold a steady output or change power levels based on what the electrical grid needs. Now that we have the turbine spinning, we need a way to turn that motion into electricity. This is the job of the generator. Think of the generator as the driven machine. It takes the mechanical energy from the turbine and converts it into the electrical energy we use every day. Inside the generator, there are two main parts: a non-movable outer shell called the stator, and a moving internal part called the rotor. The rotor is coupled directly to the turbine, sometimes with a reduction gear in between, so they spin together as one unit. The rotor is essentially a giant magnet. By passing a direct current, known as excitation current, through the rotor's windings, we create a rotating magnetic field. As this magnetic field spins rapidly inside the stator, it induces an alternating voltage in the stator's fixed windings. This is the exact moment where motion becomes electricity. To keep things running smoothly, the strength of this magnetic field must be carefully adjusted. This ensures the generator stays in perfect sync with the electrical grid. It also keeps the generator's voltage and the reactive power we supply to the grid within very specific, safe limits. The brain behind this adjustment is the automatic voltage regulator, or AVR. The AVR controls the excitation current, which in turn manages both the terminal voltage and the reactive power supply. It's a precision balancing act that ensures the power leaving the plant is stable and ready for the grid. To make the generator's magnetic field work, we need a steady supply of direct current, or DC. This is provided by the exciter. There are two main types used in these plants, brushless and static, and while they use different methods, they both perform the exact same function: feeding the energy that keeps the generator's magnetic field alive. Once the electricity is created, it needs a way out. This is where the generator bushings come in. Mounted directly on the stator housing, These bushings receive the high voltage output from the internal windings. They act as the physical connection point that allows the electric energy to be delivered from the generator to the outside world. From the bushings, the power travels through the generator breaker, which links the generator to the main step-up transformer. The transformer is a critical piece of equipment. Its main job is to step up, or match the generator's voltage to the much higher voltage of the power grid. It also acts as an electrical buffer. If a short circuit happens on the grid, the transformer protects the generator from damage. The final gatekeeper is the grid breaker. This provides the connection between the plant substation and the electrical network. In case of a massive grid failure, this breaker can disconnect the plant, allowing the gas turbine to run on island duty. This means it keeps running independently to power itself until the grid is stable again. While this is an optional piece of equipment, it's a powerful safety net for the system. And that is how a gas turbine power plant converts fuel into the electricity that powers our lives. But remember, this is only half of the story. In a combined cycle plant, we don't let the hot exhaust gas go to waste. Generating electricity from a steam power plant requires a specific cycle. The primary players here are the boiler and the steam turbine. Supporting them are the same heavy-duty electrical components we saw in the gas cycle: the generator, exciter, bushings, circuit breaker, and step-up transformer. It all starts in the boiler. This is where chemical energy from fuel is converted into heat energy. The heat is carried by combustion gases and is used to turn water into steam. It's a physical conversion process that requires a constant, steady supply of water to keep the boiler safe and the system pressurized. Once that high-pressure steam is raised, it's sent through dedicated lines to the steam turbine. The amount of steam passing through is regulated by control valves. As the steam flow strikes the blades mounted on the rotor, they begin to turn rapidly. This represents a critical energy shift. We are taking heat energy and turning it into mechanical energy. Finally, the conversion from mechanical energy to electrical energy takes place through the generator and exciter. This process is essentially identical to what we described for the gas turbine. By using both gas and steam cycles together, the plant achieves maximum efficiency. Now that we know how the individual parts work, let's look at the objective of a multi-shaft combined cycle power plant. The goal is simple: to deliver electricity with maximum efficiency. To do this, the plant uses one or more gas turbosets, one or more heat recovery steam boilers, or HRSBs, and one or more steam turbosets. These are supported by a complete water steam cycle and sophisticated control equipment to keep everything in balance. The whole process begins when the gas turboset is placed into operation. A mixture of air and fuel is ignited in the combustion chamber, creating hot gas that expands through the turbine. This causes the shaft to rotate. Because this shaft is connected to a generator, either directly or through a reduction gear, mechanical energy is immediately converted into electricity for the grid. In a standard plant, the exhaust gases leaving the turbine are at a very high temperature. If we ran this as a single cycle, that heat would simply be discharged into the atmosphere and wasted. But in a combined cycle, we direct that hot gas flow into an HRSB. Here, the waste heat is used to convert water into steam. The HRSB is the vital link that joins the gas turbine process with the water steam cycle. Once the steam reaches the correct temperature and pressure, it is sent to the steam turbine. As the steam expands through the blades, its mechanical power is transmitted via its own shaft to a generator. This provides a massive boost of additional electric power for the grid, all without burning any extra fuel. That is the power of the combined cycle. It takes what would have been waste and turns it into energy, making it one of the most effective ways to power our world today. But the story doesn't end after the steam passes through the turbine. To keep the cycle running efficiently, the exhausted steam is directed into a condenser. Here, it is cooled down and converted back into liquid water, which we call condensate. This cooling step is essential for maintaining the pressure balance of the entire system. This condensate is then sent to the feed water storage tank deaerator. This component performs three critical tasks to prepare the water for its next trip through the boiler. The water is deaerated to remove dissolved gases, preheated to save energy, and then stored until it's needed. Finally, this recycled feed water is pulled back into the heat recovery steam boiler. The amount of water used is precisely balanced to match the throughput demanded by the gas turboset's power output. With the water back in the boiler, the cycle is complete, and the plant continues to produce clean, efficient energy around the clock. Thanks for joining us for this deep dive into combined cycle technology. If you found this breakdown helpful, don't forget to like and subscribe for more engineering insights. See you in the next one.